Alright, so we're going to talk about hybridization theory now. Hybridization theory is going to help us explain bonding in these molecules. In order to understand the bonding, though, in order to understand this hybridization theory, you have to first know how to get the molecular geometries of these molecules. Okay, so there's just a table containing all the different molecular geometries we can get. Okay, because from those molecular geometries is how we're going to get this hybridization. Okay, now with hybridization theory, it's just one theory that's going to be used to explain bonding in compounds. Okay, there's other theories out there that address certain things that hybridization theory can't explain. Right? The thing to remember whenever we're dealing with bonds, remember bonds are going to occur by overlapping orbitals. So we talked about sp, d, and f orbitals. The way these bonds are going to form, we have electrons in these orbitals. They're going to be unpaired electrons in these orbitals. An orbital with one unpaired electron in one atom is going to overlap with another orbital that's got one unpaired electron in another atom to form that bond. Okay, that's how the bonding is going to occur. If we look at the location of the electrons in these orbitals and in those atoms, we can't explain how those molecular geometries can come about based upon just those overlap of those atomic orbitals, the sp, d, and f. It doesn't make sense how they arrange themselves based upon the way those orbitals are set up. So we have to come up with something called hybrid orbitals. So with hybrid orbitals, we're going to take atomic orbitals, put them together, and come up with new orbitals, these new hybrid orbitals. Okay, so if I look at an sp hybridization orbital, let's say I take a 2s and a 2p orbital, I'm going to mix them together to get two sp hybrid orbitals. For every one atomic orbital I put in, I get one hybrid orbital out. So I have one 2s orbital, one 2p orbital. So put those together, I get two sp hybrid orbitals. So those sps are two different orbitals. When we overlap them, it comes out looking like they have those two lobes. Well, that's going to help us explain some of these geometries we see. All right, so let's look at BeCl2. All right, I've got the Lewis structure there for BeCl2. And see that it's going to form one bond to each chlorine. All right, but if we look at beryllium's electron configuration, beryllium's electron configuration is just 2s2. All right, it has one set of electrons in the 2s orbital. The problem is those electrons aren't unpaired. Well, if those electrons aren't unpaired, how can they bind with the chlorine? Right, we need to have unpaired electrons. So according to this, beryllium shouldn't form any bonds. But in fact it does. So an explanation for this is we come up with these hybrid orbitals. So if I take beryllium's 2s orbital and one of beryllium's 2p orbitals, combine them together, I get two sp orbitals. Right, I still have two remaining 2p orbitals to work with, but I have two sp orbitals. Those sp hybrid orbitals are going to be at the same energy level. So when I put the two valence electrons in, each one of those boxes gets one electron. Okay, so when we look back at this picture again, the 2s and the 2p were atomic orbitals, the sp were hybrid orbitals, and when we overlap, we get that 180 degrees between the two orbitals. Well, what's beryllium's molecular geometry? It's linear. Why is it linear? Well, because when we look at those sp hybrid orbitals, they're going to be linear from each other. That's the way they're going to overlap. Okay, so if I have a linear geometry, I'm going to have sp hybridization. All right, let's look at BF3. Well, in order for boron to be able to form three bonds, it needs three unpaired electrons. Its electron configuration to start with is 2s2, 2p1, though. It only has one unpaired electron. Which means then that in order to get the BF3 structure shown there, in order to get those three bonds, I need three unpaired electrons. To do that, I'm going to take the 2s and two of the 2p orbitals, combine them all together and get three sp2 hybrid orbitals. Now each one of those sp2 hybrid orbitals gets one electron. So you can see in the bottom picture there, you can see that that sp2 hybrid orbital of boron is going to overlap with the 2p orbital of the fluorine. They're each going to have one unpaired electron, and they're going to share those electrons to form that bond. Okay, and then boron itself is going to have one 2p orbital left over. So the BF3, what's its initial electron domain geometry? It's trigonal planar. So if I have trigonal planar electron domain geometry, then I'm going to have sp2 hybridization. I've got three areas of electrons, which means I need 3 hybrid orbitals, which means I'm going to have the sp2 hybrid orbitals. All right, if I look at tetrahedral in shape, I've got 4 areas of electrons around my central atom. Well, if I've got 4 areas, if I've got 4 bonds, I need 4 unpaired electrons, which means I need to have 4 hybrid orbitals. Well, in order to get 4 hybrid orbitals, I need to take my s, 3 of my p's, to get my 4 sp3 hybrid orbitals. Okay, and you can see that that sp3 of the carbon is overlapping with the 1s orbital of the hydrogen to form those bonds. Right? Now, let's say one of those was a lone pair. Well, even doing that with nitrogen, nitrogen's 2s2, 2p3, so when I do that hybridization, I still have 4 areas of electrons around the nitrogen, which means I need 4 hybrid orbitals. So I'm going to have the sp3 hybridization. Now when I add those electrons in, though, you can see I've got a lone pair, and I've got 3 unpaired electrons. So those 3 unpaired electrons can bond with the hydrogens, and then I have the lone pair remaining on the nitrogen. All right, if I go to water, oxygen's 2s2, 2p4, right? I still have a tetrahedral electron domain geometry, so I have 4 areas of electrons around that oxygen. So I need 4 hybrid orbitals. So I've got the 4 sp3 hybrid orbitals. Now when I add electrons to it, I end up with 2 lone pairs. So you can see here, all I'm doing is deciding how many areas of electrons do I have around my central atom. That's how many hybrid orbitals I need. And then I'm just going to start with the s and keep adding on orbitals until I get to the number I need. So in this case, I need 4 areas. So I have 1 s orbital, 3 of the p orbitals. Combine them together, I get 4 sp3 hybrid orbitals. Now, if we go into something like PCl5, with PCl5, if you look at that phosphorus, it has an expanded octet. It has more than 8 electrons around it. So how are we going to be able to do that? Well, we said that in order for something to have an expanded octet, it needs access to those empty d orbitals. So anything row 3 or higher is going to have empty d orbitals it can use. This hybridization is going to use those empty d orbitals to help explain how we can get those extra electrons in there. So if I have 5 areas of electrons around phosphorus, I'm going to need 5 hybrid orbitals. So how do I get 5 hybrid orbitals? Well, I take an s, I take 3 of the p's, and 1 of the 3 d's. Put them all together. Those are 5 atomic orbitals going in. I'm going to get the 5 sp3d hybrid orbitals out. So if I have something that has a trigonal bipyramidal, it's going to be sp3d hybridization. Right, if I go to an octahedral shape, that's got 6 areas of electrons around it, which means I need 6 hybrid orbitals. Well, how do I get to 6 hybrid orbitals? I need 6 atomic orbitals. What 6 atomic orbitals am I going to use? I'm going to use the s, 3 of the p's, 2 of the d's. So I need sp3d2 hybridization around that sulfur in this picture. Okay, so hybrid orbitals in this hybridization theory are going to help explain how we can get these molecular geometries and the bonding within those compounds based upon these molecular geometries. So if it's linear, we're going to have sp hybridization. If it's trigonal planar, we're going to have sp2 hybridization. If it's tetrahedral, sp3 hybridization. Trigonal bipyramidal is sp3d hybridization. And octahedral is going to be sp3d2 hybridization. Okay, and all we're doing is taking these atomic orbitals, putting them together to get these hybrid orbitals so we can get enough unpaired electrons to get the appropriate number of bonds that we need. All right, now in terms of bonds, we have to deal with bonding types. Remember, bonds are going to be formed by overlap of these orbitals. Each orbital will have 1 unpaired electron. We overlap those 2 orbitals. We now have a pair of electrons. That's what's forming that bond. Okay, we can have overlap in the form of pi bond overlap. So if I take a p orbital and overlap it side to side with another p orbital, I can get a pi bond overlap. Now, even though it looks like there's 2 different lines there, 2 different lobes, that's just 1 bond. Okay, that's not what the cause of a double bond. It doesn't count as 2 bonds. It's just 2 orbitals overlapping to create 1 bond. It's just called a pi bond. That's the way it looks. It's that side to side overlap. Okay? If we have end-to-end overlap, that's something called a sigma bond. Okay? Those are the two types of bondings we can have. All right, so with sigma bonding, we can have overlap of s orbitals with a sigma bond, so end to end, like in H2 gas. Right, so we get the bond between the two hydrogens there. That's formed from the 1s and the 1s overlapping with the sigma bond. We could have s and p orbitals overlap. So if I take the 1s orbital from hydrogen and overlap it with the 2p orbital from fluorine, end to end, I get a sigma bond there. Right? Could also have a sigma bond formed from p orbitals, but they have to be end-to-end overlap of those p orbitals. Okay, they can't be side to side. If they're side to side, that's a pi bond. Okay, so we can have end-to-end overlap. We could also have a sigma bond formed by hybrid orbitals. Okay, now it could be hybrid orbitals overlapping with other hybrid orbitals, or it could be hybrid orbitals overlapping with atomic orbitals. So in NH3 here, I have overlap between the sp3 hybrid orbital on the nitrogen and the 1s orbital on the hydrogen to form my bond. Because it's an end-to-end overlap, that's a sigma bond. Okay, so anytime you have a single bond is always going to involve a sigma bond. Okay, it's one type of those overlaps. Okay, we can never have a single bond be a pi bond. Okay, it's just not going to occur. So with the pi bond, remember, it's that side-to-side overlap of p orbitals. And we're only going to have p orbitals do this side-to-side overlap to get this pi bond. Okay, this we're going to see occur in double and triple bonds. All right, so let's take a look at the picture of this. So if I think about double bonds, let's look at an example here. So I have the C2H4 example. There's a double bond between the carbon and the carbon. So what's causing that double bond? Well, if we look at a picture of all the orbitals involved here, if I look around that carbon's got 3 areas of electrons around it, right? Which means I'm going to have 3 hybrid orbitals, so I'm going to have sp2 hybridization. So on each carbon I have sp2 hybridization. Well, one of those lines there, one of those bonds, is represented by a sigma bond where the sp2 hybrid orbital from one carbon overlaps with the sp2 hybrid orbital from another carbon, end to end. Okay, that's a sigma bond. That's one of those lines in the double bond. The other line represented in the double bond is going to involve that pi overlap, that pi bond. So on each carbon, I used its s and 2 of its p atomic orbitals to get the sp2 hybrid orbitals. But that means I have a 2p orbital left over. Okay, because each one of those has a 2p orbital left over, as we form those bonds, those 2p orbitals on the carbons then can overlap. When those 2p orbitals overlap, we get that second line there, that second bond. Okay, so one of those lines in the double bond is sigma bond, the other one is a pi bond. The sigma in this case is the sp2 overlapping with the sp2. The pi is the 2p overlapping with the other 2p. Okay, so we have our sigma position, and we have our pi overlap. Okay, now a simpler way just to see the pi overlap, okay, you can see that that's the second bond being formed. So that first line drawn there is for that sigma overlap. Now we just see the pi overlap. Okay, and you notice on here too, we could talk about the other bonds as well. So what's the overlap between the hydrogen and the carbons? Well, the hydrogen's 1s orbital is overlapping with the sp2 hybrid orbital of the carbon. So let's look at another example of this. All right, now if we look at these carbons, each carbon has 2 areas of electrons around it. Since I have 2 areas of electrons, I'm going to have sp hybridization around those carbons. All right, well, if I have sp hybridization, that means I've only used up one of my p orbitals. I have 2 p orbitals left over. So when I look at this, one of those bonds is going to be a sigma bond due to the sp orbital on one carbon overlapping with the sp orbital on the other carbon. A second one of those bonds in the triple bond is going to form from one set of the 2p orbitals overlapping with each other to form a pi bond. And the third one then is going to be a second set of 2p orbitals overlapping to form a pi bond. Now, if I don't have those extra p orbitals left over, I'm not going to get a triple bond. So if I have something that has sp2 hybridization, I can't get a triple bond with it because I don't have enough p orbitals to overlap. If I have something that has sp3 hybridization, I can't even form a double bond because I can't get any pi bond overlap. I have no p orbitals left over. So with this triple bond, one of those lines represents a sigma overlap, one of those lines represents a pi overlap, and then the third one represents a pi overlap. All right, if we just break out the p orbital overlaps, you can see here we get two different p orbitals. Now, another thing we have to worry about is something dealing with resonance structures and this delocalized pi bonding. All right, resonance structures, if you remember, involve double bonds that could move around. Okay, if we look at benzene here, benzene has double bonds that can move between the different carbons. That's because each one of these carbons has a free 2p atomic orbital left over, right? Each one of these carbons has 3 areas of electrons around it, so it's sp2 hybridization. Each one of those has a p orbital free, so instead of saying one p orbital overlaps with another p orbital to form a single double bond, we actually get all of them overlapping together to get what we call delocalized pi bonds. Okay, so with these resonance structures, those electrons in those double bonds are actually delocalized. They can move throughout the entire thing, in that entire system involving those p orbitals. Okay, so it's going to involve that delocalized pi bonding. But once again, if we don't have access to those p orbitals, we're not going to get this delocalized pi bonding. We won't get double bonds. Those double and triple bonds are going to involve those p orbitals. All right, remember, every 2 atoms share at least 2 electrons in order to form a bond. A bond between 2 atoms that represents 2 electrons, and they're sharing them. If we have 2 electrons between atoms on the same axis of the nuclei, those are going to be sigma bonds. Those are going to involve those end-to-end overlap of orbitals. That can occur with a wide variety of orbitals. Those sigma bonds are always going to be localized. In other words, those electrons are going to stay between those 2 specific nuclei that they're forming that bond between. All right, if we have double and triple bonds formed, those second and third bonds are going to be pi bonds between p orbitals. And if we have resonance structures then, that's going to involve those double bonds that can move around. We're going to get delocalization of those electrons. So they're not fixed specifically between any 2 atoms. They're actually delocalized throughout the entire system. Okay, but that's going to take us to the end of hybridization theory. So based upon the geometry, you should be able to predict what hybridization you have. And it's just a matter of how many areas of electrons do you have around the atom of interest. You just keep adding atomic orbitals until you get to that same number of areas. So if I have 2, it's sp hybridization. If I have 3, it's sp2 hybridization. If I have 4 areas, it's sp3 hybridization. If I have 5 areas, it's sp3d. If I have 6 areas, it's sp3d2. Okay, so that's how we're going to predict hybridization in these molecules.